Hello there, welcome to this video where we'll be unpacking implicit differentiation and how to follow the correct procedure to ensure that you are effective in this method of differentiating. Okay, so now if I give you the following, y is equal to x squared, y is equal to negative 2x minus 7, y is equal to e to the x, y is equal to the absolute value of x plus 3. This is what you call explicit equations. Y is explicitly written in terms of x. Okay, but what we are discussing in this video is not explicit equations, it's implicit equations. Okay, and they look like this. If I now give you x squared plus y squared is equal to 36. Y is not written as the subject of the equation like this other set of equations I've given. So this is what you call an implicit equation. Okay, and we have learned how to differentiate explicit equations using the respective differentiation rules. So in this video, I want to help you learn how to differentiate equations that look like this. Okay, so this, of course, we know it represents a circle with radius of 6, and circles are not functions because they fail the vertical line test. However, they are still part and parcel of the different equations that we engage with when we discuss implicit differentiations. Okay, so now I'm going to offer 3 examples that pertains to implicit differentiation, and one will contain a problem on a tangent. Okay, so let's go for it. Right, so here are the first 2 examples, and we are asked to find dy over dx for these 2 equations. Now, the procedure to follow is that step 1, you need to differentiate both sides. Okay, so in other words, find dy over dx for your left hand side and dy over dx for your right hand side. That is the standard way to approach implicit equations when you differentiate. Okay, this is sum of functions, so we're going to bring in the sum rule. When you differentiate x squared with respect to x, we get 2x plus, now we do differentiate y squared with respect to x. We know that in this equation we can definitely write y as the subject of this equation explicitly, so that it means we need to introduce the chain rule, okay, because y will be plus or minus square root of 36 minus x, so you end up with an in and outer function. Okay, and we're going to apply the Leibniz notation here and write dy over dy of y squared times dy over dx. Okay, so actually the product of this gives you dy over dx, right? Which is equal to, when you derive 36 with respect to x, a constant, so you get 0. Okay, so we end up with 2x plus 2y times dy over dx, which is equal to 0. This is what we want to find. Okay, and we need to isolate that by transposing the other 2 terms. 2y times dy over dx will be equal to negative 2x. Alright, and we divide by 2y both sides, and therefore dy over dx will be equal to negative x over y. Okay, so that represents the rate of change, okay, or the gradient function for this equation, okay, which can be used to find tangents and equations of tangents, as well as the gradients for tangents. So yeah, this is basically the procedure to have the dy over dx maintained throughout your algebraic process, but use the chain rule whenever you work with y. Don't regard it as a constant, it is still a variable, and therefore chain rule applies whenever you deal with y. Okay, this takes care of example 1. Example 2, we approach it the same way. So let's use a different notation here. We want to differentiate the left-hand side, x squared minus xy plus y squared, and differentiate the right-hand side. Okay? So when you differentiate that, you get 2x minus x times y. So it's a product of functions, so we need the product rule. And the product rule says you're going to differentiate the first function x with respect to x, so that is 1. Okay, you multiply the second function y plus, okay, you keep your first function x, you multiply it with the derivative of y with respect to x, but now we need to work with the chain rule. So that will be the derivative of y will be 1 times dy over dx. Okay, and that takes care of that part, the chain rule, plus the derivative of y squared, the same thing applies there. 2y times dy over dx is equal to 0. Okay, so we need to carefully clean up here. We have 2x minus y minus x times dy over dx, okay, plus 2y times dy over dx equal to 0. Okay, so we're going to transpose this 2 and factor out the dy over dx. So 2x minus y is equal to dy over dx. And when you do that, you end up with x minus 2y that remains. And you need to divide both sides then by x minus 2y, x minus 2y. Right, and that will cancel. And you are left with that as the expression for dy over dx. dy over dx will be equal to 2x minus y over x minus 2y. Okay, so this takes care of example 2. Now let's bring in a question that has to do with tangents, but still under implicit differentiation. Question 3. Okay, let's go for it. Okay, so this is question 3. Determine the equation of the tangent to the curve x squared minus x sine y equal to y plus 2x at the point 2, 0. What do we need first? To implicitly differentiate this function here. So let's differentiate the left and differentiate the right hand side. Okay. Difference of functions there, but it's a product rule there. We need to be careful with that. So differentiating x squared, we get 2x minus, let's introduce brackets for this product rule, derivative of x, get 1 times sine y, plus, keep the x, derivative of sine y, or y, again, we need the chain rule to apply there. So we end up with the following: cos y times dy over dx, all right, is equal to derivative of y with respect to x. This gives us 1 times dy over dx plus the derivative of 2x with respect to x will just be 2. Let us carefully clean up here. This is 2x minus sine y minus x cos y dy over dx is equal to dy over dx plus 2. Transpose the 2 and take this guy to the right hand side. We have 2x minus sine y minus 2 is equal to dy over dx. We factor out the dy over dx 1. Now to the minus becomes a plus the x cos y. Alright? Divide both sides by 1 plus x cos y cancellation there, and therefore dy over dx is equal to 2x minus sine y minus 2 over 1 plus x cos y. Where are we evaluating? At the point where x is equal to 2. So we want to evaluate dy over dx at x equal to 2, which means that we're just going to sub in here, and y equal to 0. We're going to sub in obviously the correct letters here. So, I mean, the correct numbers for each variable. So 2 times 2 minus sine 0 minus 2 over 1 plus 2 times cos of 0. So this will be 4 minus 2 and 1 plus 2, 2 over 3. And that is the derivative at that point, which will represent the gradient of the tangent. What do we need now? We need the equation of the tangent. You can just close off by doing this. Y minus 0 is equal to 2 over 3, x minus 2, and therefore the equation of the tangent will be 2 over 3x minus 4 over 3. Okay, so that is the full solution for this question. Okay, hope you enjoyed it and it was crystal clear for you. So do more of such types of questions so that you can be effective at implicit differentiation. Thank you very much for tuning in and watching the video. I'll see you in the next set of videos. Keep well.